Hello, we are going over test 2 review, and I will take you to another session where I go over 1 through 9, and then I'll bring you back and we will go over these 3 in number 10.
Well, what we see in this first one, the numerator, we always think about this with the inverse tangent. It sits between minus pi over 2 and pi over 2. And so what I can say here, certainly starting at k equals 1, the numerator is positive, okay, because tan inverse of 0 is 0, and then it's increasing after that. So we can say the following, that 0 less than or equal to except it's k to the 4th. And this is less than or equal to, as I just mentioned, tan inverse is less than or equal to pi over 2. And we also know, for example, the limit as k goes to infinity is equal to pi over 2. But now, if you look at this series, this is the comment I will make. It's a constant times a convergent P series. Where P is 4, bigger than 1. And this is all part of the justification. And so what do we have? We have our series is non-negative and term by term less than or equal to a series that is convergent. This is comparison test. This k equals 1 to infinity. This converges. Now, is this the only way you could have done this? Well, absolutely not. For example, you could do limit comparison with the P series 1 over k to the 4th. This would also work. You would get, if you took tan inverse k over k to the 4th divided by 1 over k to the 4th, took the limit as k goes to infinity, we would get pi over 2, which is positive and less than infinity. So limit comparison will work in this example also, but the way I have done it is fine. I see factorials. This is telling me ratio test. So what we want to do in B is look at the absolute value, ak plus 1 over ak. And first, I'm going to simplify this. Then once it's simplified, I will take a limit as k goes to infinity. Well, here, look, ak is always positive, and so I don't really need the absolute values, so I will just write it this way, k plus 1 to the 100 divided by, well, this would be k plus 2 factorial. There is ak plus 1, and then we divide by k to the 100 over k plus 1 factorial. Okay, then I will, let's see if I can move this up some. Okay. I will invert and multiply because I have fraction divided by fraction, and I'm going to line everything up so that things, we can easily see what goes with each other and what will cancel. So in my numerator, I have k plus 1 to the 100. I also have a k plus 1 factorial. In my denominator, I have a k to the 100, and I have a k plus 2 factorial. And then Well, k plus 2 factorial, maybe I'll write this over here in the side as a comment. This is a kind of property we use a lot when we see, well, factorials. This is k plus 2 times k plus 1 factorial. Okay, so in the denominator, I have a k plus 2 times k plus 1 factorial, and it will cancel with the k plus 1 factorial in my numerator. So let me, maybe I'll erase this now that I have discussed it. And I will get, well, this first one is something all to the 100. This will be k plus 1 over k all to the 100. And then I have a k plus 2 here. Okay? Now this is as simplified as I can make it at the moment. So now I will take a limit. I take a limit as k goes to infinity of k plus 1 over k to the 100. Well, maybe I should, well, let me go ahead and write this, and then I will add what I meant to write. Let me move this over. Okay, I meant to write a limit as k goes to infinity of this. This is what we need for the ratio test. You take a limit, k goes to infinity, absolute value, ak plus 1 over ak. And this will be a limit. I just added that to show one more step. K goes to infinity of this. We've already simplified. Okay, now we have to think about this, and maybe I will move to red. This, we know what's happening. Uh-oh, here. As k goes to infinity, this, while the denominator is growing without bound, this is going to 0. Now, what about this term? As k goes to infinity, or maybe I'll just underline it. Well, first of all, the function x to the 100 is continuous, which means we can bring the limit inside. And inside, k plus 1 over k is going to 1. So this term is going to 1 to the 100, which is 1. Okay? So now we have, while both the limits exist, this is property of limits. If both limits exist, and then the limit of the product goes to the product of the limit. So this will go to 1 times 0, which is 0, which is less than 1. By the ratio test, this series, k to the 100 over k plus 1 factorial converges. Okay, when we have this limit, the ratio test says, and you have this on that series sheet that I provided you, when this limit is strictly less than 1, we get convergence. If we got the limit was bigger than 1, we would know divergence. And if we had the limit was equal 1, we would have to use another test. Okay, now we move on. This series, if you think about what's dominating, is this and this. So this series, let me do this. It looks like what I have circled. Just subtracting 1 in the denominator for k very large is really not going to affect anything, but that alone is not justification. Okay, so, but it gives us intuition. So let's look at this series. 2 to the k over e to the k. This is a sum, k equals 1 to infinity of 2 over e to the k. This series is geometric. This series has, well, the initial term is 2 over e. What matters for convergence or divergence is the ratio r, which is 2 over e, absolute value of r. 2 over e less than 1 converges. Okay. If I try to use direct comparison, here's what I would do. Well, I'm comparing to a convergent series, so I would need this to be here. And I would need to put this series here. So the question is this true? I have seen so many people, so many times people try to use comparison tests when they can't. And so I'd like to think about what's happening here. Well, this is the issue. This is a smaller denominator. Smaller denominator means bigger fraction. So this actually, oops, this one, not true. But what is true is this way, and I'll make this thicker. Smaller denominator, bigger fraction. Now, comparison test. This part, we don't have any information because it goes the wrong way, okay? We need to be less than or equal to convergent series, term by term, in order to use the normal comparison test. But that's okay. This is just not the right test. What we want to use here is limit comparison. So we take a limit as k goes to infinity of 2 to the k over e to the k minus 1 divided by 2 to the k over e to the k. And then if this limit is positive and less than infinity, both series have the same behavior. And since I've already justified that this geometric series converges, I will get that this series converges. So let's calculate this limit. Well, I will invert and multiply. From the denominator, I will get a 2 to the k, e to the k over. I will get a 2 to the k, e to the k minus 2 to the k. And now, for example, if you're not sure what's going on with this limit, here's what we can do. We can, and you might remember this from Calc 1, let's just divide everything by this 2 to the k, e to the k. Or you can make it one big 2e to the k if you wanted to. When I do this, I get 1 over 1 minus 1 over e to the k. I've just divided every term by this 2 to the k times e to the k, and now this limit is easier to see what's happening because this part goes to 0, and everything else we see is just ones. So this limit is 1, which is bigger than 0, less than infinity. Okay, so by the limit comparison test, this series k equals 1 to infinity of 2 to the k over e to the k minus 1 converges. But this is one where we could not, as I mentioned, we could not use the normal comparison test because it doesn't work out the way that we need it to. Well, what do we see in D? We see a function all to the k. Root test. Okay, this is telling us to use the root test because we see something all to the k. Very nice. So what I'm going to do here is, I have enough space. I'm at the bottom of the page, but I do in fact have enough space. I take a look at the kth root, absolute value of ak. Okay, well, ak is always non-negative, so I can kind of disregard the absolute values or just think that the absolute value of ak is ak itself, and we get k over ln k. This is ak, and then to the 1 over k. And this is k over ln k. Okay, then using the root test, we want to take a limit as k goes to infinity. of the kth root, absolute value of ak. This is a limit as k goes to infinity of k over ln k. Right, we've already simplified this. Now, think about your growth rates. Polynomial, which k is, grows significantly faster or greater, it's bigger than ln k when you get close to infinity. Or you could say ln k grows significantly slower than k. So what is this limit? Well, it's infinity, which is without a doubt bigger than 1 by the root test. This series diverges. Okay, determine whether the series is absolutely convergent, conditionally convergent, or divergent. Now, if I quickly just glance at the terms and see, are they going to 0? This would help me address this part, right? I usually look at this first. If the terms are not going to 0, term test, we're finished. But here, if you look at these terms, in fact, the kth term, as k goes to infinity, goes to 0. So I cannot use the term test. Now next, I'm going to look at this one. Is it absolutely convergent? So let us figure that out. If that fails, then I would do a alternating series test. So let's look at absolute value of ak, which is 1 over k squared plus 9. If I look at this sum, this will, let me make that a little easier to see, this will converge. And we have a few ways we can see this. Number one, integral test. We could integrate 1 over k squared plus 9, or 1 over x squared plus 9. We get 1/3 tan inverse x over 3, and then you could calculate this improper integral. I tend to use integral test only when I need to. If something else strikes me as being easier, then I would do that, so I don't have to integrate. And in fact, with this one, you notice that this series converges as it is a p series with p equals 2, greater than 1. P series, p equals 2, bigger than 1. And let me move this back a little bit. And we have that 0 is less than or equal to this, which is less than or equal to 1 over k squared. Right? Because bigger denominator means smaller fraction. Okay, so by the comparison test, we have shown this, k equals 1 to infinity, absolute value of ak, converges, which means we have an answer here. Maybe I'll put it on the same line in red. We know the original series is absolutely convergence. Absolutely convergent or absolute convergence, because what we have justified is that the absolute value, you take the absolute value of the terms and that series converges. Okay, so we're finished with this one. We don't need an alternating series test because we have our answer. Now let's move into B. If we look at, so first of all, glance at the terms. Are they going to 0? Yes, they are. We can't use a term test. then I would naturally ask myself, is it absolutely convergent? So if we take the absolute value of an, we get 1 over ln of n. And this series, if we use the hint, what does that say with 1 over? Well, look, if the natural log is less than x, when you take 1 over, what will happen is this switches, okay? So we have this, that 0 is less than or equal to 1 over x is less than or equal to 1 over, I need an n, 1 over ln of n. Okay, this comes from the hint. And the sum n equals 1 to infinity, 1 over n diverges y harmonic series, or you can say it's a p series with p equals 1, but just quoting the harmonic series is perfectly fine. Okay, so then what does that say? This says the sum k equals 2 to infinity of absolute value of an diverges by the comparison test. We are bigger than, term by term, larger than a divergent series. Comparison test says you diverge. Now, we don't have the answer yet. All we know is that this does not happen for this series. It's not absolutely convergent because the absolute value diverges. But maybe this is true, okay? And in fact, it will be. Here comes the alternating series test. Alternating series test. What do we need for the alternating series test? We know that an is, absolute value of an is 1 over ln of n. We know that this satisfies absolute value an plus 1 is less than absolute value of an because, well, the denominator is growing. Natural log increases. Okay, it's decreasing. And then the limit as n goes to infinity, absolute value of an, this is 0. Okay, so then this is all we need. We need, number 1, it needs to be alternating, which it is. Number 2, in absolute value, the terms must be decreasing, and then absolute value of the terms must go to 0. And then we have our conclusion. By the alternating series test, the sum n equals 2 to infinity minus 1 to the n over ln of n converges. And so we get conditional convergence. This is exactly what conditional convergence is. It's when the absolute value, term by term, you take the absolute value of the terms, that series diverges, but the series itself, using alternating series test, converges. This is conditional convergence. Now, I have a warning on that sheet I handed you that this test will never tell you which type of convergence you have, okay? I couldn't have just used this test and then say conditional convergence. The alternating series test doesn't say anything about the absolute value here. It doesn't say anything about this series, which is why here, when I had absolute convergence, I did not justify it with an alternating series test, because the alternating series test only tells you something about the alternating series. Does it converge? Does it diverge? That's all you get. You don't know anything about the absolute value, take the absolute value of the terms, that series. So to be able to specify, are you this type of convergence or are you this type of convergence? Yeah, the alternating series test will never tell you the difference. That's why you notice this one was easier, because once I knew the absolute value converged, well, you take the absolute value of the terms, that series converged, then I was done. But here, when I took the absolute value of the terms, look at that series diverges, I still had to do some more work to figure out I was conditionally convergent. Okay, number 3, we want to find the radius and interval of convergence for this power series. Ratio test. Okay, so here we go. We look at the absolute value, ak plus 1 over ak. 3 to the k is non-negative, square root k is non-negative, and so we really just need absolute value on this part. And then we have divided by 3 to the k plus 1, square root k plus 1, and then we divide by absolute value x minus 2 to the k over 3 to the k, square root k. Okay, now, just as when I simplified absolute value ak plus 1 over ak before, I'm going to line things up to help myself out. So what do I have in the numerator? I have an absolute value x minus 2 to the k plus 1. In the numerator, I also have a 3 to the k and a square root k. This is all numerator, and then divided by, in the denominator, I have an absolute value x minus 2 to the k. I have 3 to the k plus 1, and I have square root k plus 1. And now, okay, this is when everything gets beautiful, because I am left with, in my numerator, I have absolute value x minus 2. In the denominator, I have a 3, and then I have a big square root of k over k plus 1. And this is simplified. Now I will take a limit. Now I take a limit as k goes to infinity, absolute value ak plus 1 over ak. And I get a limit as k goes to infinity of absolute value x minus 2 over 3 square root k over k plus 1. And now let's think about what's happening here. First of all, this part, there's no k here. Okay, you could just pull this outside of the limit if you wanted to, although you could just think with respect to k, this is just constant number. And then here is what has the k. Again, kind of like when we had to the 100 power, the square root is a continuous function. We may bring the limit inside. Inside, that's going to 1. So the limit of this part, and maybe now I will write, this part goes to the square root of 1, which is 1. And so I have my limit here. This limit is absolute value x minus 2 over 3. Using the ratio test, I need this limit to be less than 1. Using the ratio test for convergence. Or absolute value x minus 2 less than 3. And this is what will tell us the capital R. Okay, because it was a theorem that when you have absolute value x minus the center less than some number, and that's what you know for convergence, and you know if you're bigger than that number diverges, then that means this is the radius of convergence. So capital R is 3. And what we know so far is, let me draw a number line. We know here is the center, 2. And we move out in each direction by the radius. This would be 5, and this would be minus 1. And so far, we don't know anything happening at the endpoints, but we are guaranteed convergence here. Okay? And what we need to figure out is, does the power series converge at 5 and at minus 1? Okay, then we will be finished. So we have the radius, but now we need the interval. Okay, so let's test these two. typically I will write the two, both of them, and then I will figure out what's happening. So at x equals 5, sum k equals, let's see, 2 to infinity. We have 5 minus 2 to the k over 3 to the k, square root k. It's this, the sum, k equals 2 to infinity of 1 over square root k. Now, maybe over here, I will do the other one. At the other endpoint, x equals minus 1. Let's write out the power series. Well, we have a sum, k equals 2 to infinity of, we have minus 1 minus 2 is minus 3 to the k over 3 to the k square root k, which is a sum, k equals 2 to infinity. We get a minus 1 to the k over square root k. Okay, so what I need to do is figure out, does this series converge or diverge? That will tell me what's happening at the endpoint, x equals 5. Does this series converge or diverge? That will tell me what's happening at the endpoint, x equals minus 1. Well, let's see. This one, and make sure on an exam you test your endpoints. It's a very important part of the problem. This one, this is a p series. P equals 1/2, less than or equal to 1, diverges. Okay, so we know it diverges at 5. This one, well, alternating series test, absolute value, maybe I'll just write the absolute value. 1 over square root k satisfies. We need two things. 1 over square root k plus 1. So it's decreasing. And the limit as k goes to infinity, 1 over square root k is 0. Okay, so we get that this converges. Alternating series converges by the alternating series test. Okay, so what do we know? If I go back and I highlight, I know it converges at minus 1, and maybe I'll diverges, colored a different color, at 5. So now let's write the interval of convergence. Maybe I'll do it in gray. It converges at minus 1, diverges at 5. This is the interval. And, oops. This is R is 3. This is number 3. Now, you might look at this and say, I don't see exactly x minus the center to the k. So how is this a power series? Well, let's do an initial step to look at this. What do we see here? If we work with just this numerator, this equals, well, if I factor out a 5 to the k, I get x minus 3 over 5 to the k. So in fact, this is a power series. The center of this power series is a equals 3 over 5. That's an important thing to realize, because you always need to figure out what is your center. It will help you, because once you have the radius, you move in each direction from the center, and you'll figure out, for instance, the endpoints. So this is a power series centered at 3 over 5. And now let's start with the ratio test. We look at absolute value, ak plus 1 over ak. And, well, this is a 5 to the k plus 1. Absolute value, x minus 3 over 5 to the k plus 1 over k plus 1. And then we divide by 5 to the k, absolute value, x minus 3 over 5 to the k over k. And then, just like the last example, and very similar to the other ratio test example, I'm going to line everything up when I invert and multiply. I have a 5 to the k plus 1 in the numerator. I have absolute value x minus 3/5 to the k plus 1 in the numerator, and I have a k in the numerator. Then here I have a 5 to the k, absolute value x minus 3/5 to the k, and a k plus 1. Okay, now this is when the magic happens. We get a 5, absolute value, absolute value x minus 3/5. And then we have times k over k plus 1. Now I'm ready to take a limit. We take a limit as k goes to infinity. Absolute value, ak plus 1 over ak. This part here, there is no k in this first part. Okay, with respect to k, it's a constant. So I'm really just looking at the limit of this, and k plus 1 over k, this goes to 1. Okay, now I see what my limit is. This limit is 5, absolute value x minus 3/5, which again, set it less than 1 for convergence. And I already mentioned ratio test. So now, CE. Now you multiply through by 1/5. We get absolute value x minus 3/5 less than 1 over 5. And you see here, this is what gives us our radius. Capital R is 1 over 5. But don't stop here. We have found part of it, but remember, we still have to test the endpoints. I've seen a lot of students don't show any work for testing the endpoints, and then you lose a lot of the points of the problem because, well, what do I have? Here's my number line. This was part of the initial step. My center is 3/5. Now I move in each direction by 1/5. This will be 4/5. This will be 2/5. Okay, and then, well, I can do this again. Okay, so far I have no idea. I have no idea. And guaranteed converges on this open interval. What's left is test the endpoints. Okay, so here we go. This is the final part of this problem. We were going to test at x equals 2/5. What is my power series? It's a sum. K equals 1 to infinity. Well, I have 2/5 minus 3/5. Maybe I'll write it. I have a 5 to the k. I have a minus 1/5 to the k over k, which is a sum. K equals 1 to infinity minus 1 to the k over k. And then I will immediately just write down the other endpoint at x equals 4/5. I get the sum. I have 5 to the k. I have 1/5 to the k and over k. And this is a sum. Now, it looks like in this one also that we're going to have one converging, one diverging. Doesn't always happen that way. Sometimes you have open on both endpoints. Sometimes you have closed on both endpoints. That's why we have to test the endpoints. You cannot know what's happening at the endpoints just by performing a ratio test. But what we see here, this is the alternating harmonic series. It converges. Or if you don't want to quote that, you can use alternating series test. And this one is the harmonic series, diverges. You could also say it's a P series with P equals 1, less than or equal to 1, diverges. But when I see the harmonic series, I usually quote the harmonic series. So we get, in this example, we get, let's see, diverges here and converges here. So my interval, this is the final, we have closed 2/5 to 4/5. Open. And then here is the radius of convergence. Okay, now we move into the applications. Well, what do we see here? This one, we have motion along a line. And here's the velocity function. And we want to calculate both the distance traveled and displacement. Well, here is how we calculate distance traveled for motion along a line. We integrate the absolute value of the velocity. So what we need to do, sort of as side work, is figure out when this velocity function is positive and negative. I will first set this equal to 0. And this one's not too terribly hard. We factor out a t, and we have 2 minus t. And then, so for example, it's 0 at, it's 0 at 0 and 2, okay? 0 is already an endpoint of my interval, so I can make a little chart, t, 2 minus t, and then here will be, we could test on each side of 2, for instance, at 1 and at 3. You could also figure out where this is positive and where this is negative by graphing the function, for example. So here at 1, t is positive and 2 minus t is positive. The velocity is positive. At 3, t is positive, 2 minus t is negative. The velocity is negative. This tells us exactly how to set up our integral. It's going to be an integral from 0 to 2. Well, between 0 and 2, we see the velocity is positive. So it is 2t minus t squared dt. And then plus, it will be an integral 2 to 4 of t squared minus 2t dt. So this is what I want to integrate. Now, both of these, while they have very similar antiderivatives, right? So this will be, we get t squared minus t cubed over 3, and these are evaluated between 0 and 2, and then plus we have t cubed over 3 minus t squared, evaluated between 2 and 4. Now, don't think that everything here is going to cancel out, because it doesn't. So we get 4 minus 8/3, and then evaluate at 0, we get 0. And then we evaluate at 4. 4 cubed is 64 thirds minus 16. And then we subtract, we have 8/3 minus 4. 64 thirds, I'm going to do the thirds part first. 64 minus 16 over 3. And then we have minus 16 plus 8, 48 over 3. And then minus 8, 8. This is the total distance traveled, part A. Now for part B, and this part takes, well, less steps, because all we do here, the displacement, this is just the shift in position, and we just integrate the function. So we integrate, no absolute value needed here. Again, we have t squared minus t cubed over 3 evaluated between 0 and 4. In fact, we've already evaluated this at 4 above, but we can do it again. We get 16 minus 64 over 3. And then when we subtract off evaluating at 0, we get 0, negative 16 thirds, like this. Number 6 is arc length. What we want to do here is begin with 1 plus, so I've got to give this a function. Say I call this g of y. Okay, now we have x, the function of y here. It's fine. Nothing has changed. We can work with it this way. So what we want is 1 plus the derivative squared. And I simplify. And then once this is simplified, I put this under a square root and integrate. Okay, so 1 plus, I'll put big parentheses and then squared. The derivative here is 3y minus 1 to the 1/2. And now I square this and I get 1 plus 9y minus 1, which is 9y minus 8. Okay, this is the simplified 1 plus the derivative squared. Now, arc length is an integral. 1 to 12 of the square root of 1 plus the derivative squared, which is 9y minus 8. Make that a little big, and then dy. Okay? This is something we can integrate. U is 9y minus 8. This is substitution, right? So du, 9 dy, just dy will be 1 over 9 du. And then this integral goes from y equals 1. U will be 9 times 1 minus 8, 1. And when y equals 12, u equals, 9 times 12, maybe I'll write that as an intermediate step, minus 8. U will be 100. Okay, this is my side work for substitution. I have an integral. It goes from 1 to 100. And we have the square root of u times 1 over 9 du, which is 1 over 9. We add a power, divide by the higher power, like this. When we divide by 3/2, it's the same as multiplying by 2/3. And then we evaluate between u is 1 and 100. Okay, so we get 2 over 27. And then we have 100 to the 3/2 minus 1 to the 3/2. But this is something I can actually calculate. The square root of 100 is 10, and then cube it, 1,000. So we get 2 over 27, 1,000 minus 1. So this one works out as an actual integer. Okay, very nice, 74. Okay, here is the answer to this one. Number 7, what do we see here? We have a particle moving in space. And I think I found this one off an old final. It asks a little bit different than some of the textbooks, so exercises, so it's good to think about. First of all, we need distance traveled. And then instead of just asking, let me point to this. Instead of just asking for displacement, as we have practiced many times, we ask distance traveled and then the magnitude of the displacement vector. Okay, so we're going to need to calculate distance traveled, okay, and displacement. Very nice. Then to answer B completely, we need the magnitude of displacement. Well, distance traveled, let's write the formula. It's an integral, will be 0 to 3. Now, this isn't absolute value, this is magnitude or length of the velocity vector. So the first thing we need here is to compute the velocity vector. This will be, let's see, it's going to be 6t cubed, and then 3t to the 5th, then 8t cubed. I just differentiate each component, and then the derivative of the +3, the derivative of the -7, those are 0. Okay, now I need to compute the length. This will be the square root of, well, you add up the squares of each component. So this is 36 t to the 6 plus 9 t to the, when you square it, it's 10th. Power to a power, multiply powers, and then 64 t to the 6th. Okay, let's combine like terms. We get a square root. 36 and 64 gives us 100, so we have 100 t to the 6th plus 9 t to the 10th. Now, it might seem like, well, what am I going to do? Because this doesn't look like something I'm prepared to integrate. But what we want to do here is factor out what's common to both. Both of these have t to the 6th. First, I'm going to put t to the 6th, and then I have 100 plus 9. This would be t to the 4th. And now if I bring out a t to the 6th, well, you take the square root, you get t cubed. And then I have 100 plus 9 t to the 4th. And here is where we start to realize that this is something we can integrate, because look, inside function, 100 plus 9 t to the 4th. The derivative of the inside function, look, we see a multiple of the derivative right here. So this is substitution. We have an interval 0 to 3, t cubed square root 100 plus 9 t to the 4th dt. U is 100 plus 9 t to the 4th. du is 36 t cubed dt. We have t cubed dt, which is 1 over 36. Uh-oh, pardon me. I wrote dt and said du. It didn't make a lot of sense as I wrote it. I said it correctly and wrote it wrong. Du is, take the derivative, 36t cubed dt. And then 1 over 36 du is what we have in our integral. It's t cubed dt. T goes from 0 to 3. When t is 0, u is 100 plus 0, 100. When t is 3, u is 729 plus 100. So my upper limit of integration is 829. Now let's go back to this definite interval. This is an interval. It goes from 100 to 829 of the square root of u times 1 over 36 du. So this is 1 over 36. It's the same function that we integrated in the last example. We get 2/3 u to the 3/2 evaluated between 100 and 829. Okay? And then this is 1 over 54. And then we have 829 to the, 29 to the 3/2 minus, again, is 100 to the 3/2, which is 1,000. And I think I'm just going to leave my answer like this. We know generally displacement is this integral. Let's see, 0 to 3 of, well, it would be 0 to 3 here, but it's an integral of velocity. Now, you could also just take, let me just mention this, take p of 3 minus p of 0. And you get the same thing, okay? Because this is what displacement is. It's a shift in position. So you could evaluate this position function, which we are already given at 3 and at 0. Take the difference okay? Or you can integrate the velocity. We've had to find that in part A. You really have some choices. I think I'm going to integrate velocity only because I don't have to worry about this plus 3 and this minus 7. And once I integrate velocity, I'm going to have something that is 0 at 0. So I can just evaluate at 3 and be done with it. Okay, so when I integrate this, it's 3/2 t to the 4th. This is 1/6 t to the 6th. And this is 2t to the 4th. You see, just as I was saying as a comment, this is not the position, but the position and what I have found, this antiderivative, differ by a constant. This is the way, as we know, integration works. But then I evaluate this here. So I have 3/2 times 81, which is 3 to the 4th. And then I have 1/2 times 3 to the 6th. And then I have 2 times 81. This is displacement, but what we want is the magnitude of this, which is a square root of 9/4 81 squared plus 1/4 729 squared plus, well, this will be 4 times 81 squared. You just square each part. Now, here's where I'm going to use a calculator. We get this as approximately 416.97. Okay, well, let's move into the volume. We have 2 problems involving volume. Now, let me just start with this region. What do we see? Well, it's bound by y equals x and y equals x squared minus 3x plus 3. And there's a few ways you can go about it. Way number 1, and you see I have included the picture twice because I'm going to do part A and part B. But way number 1, which is perfectly fine, I just graph it. I use Desmos. You could use your graphing calculator. And when I do, I see these 2 points of intersection, right? I see 1, 1, I see 3, 3 as the points. Okay, fine. Well, another thing you can do is here, to figure out the x values where the 2 curves are equal, you just set them equal to each other, and then I subtract x from both sides, and I have a quadratic equal to 0, which I can factor. And I get that x is 1 or 3, and then to get the points on the graph, you can, well, evaluate either side. Really, evaluating y equals x is a little easier, but you see the points would be 1, 1, and 3, 3. That's solving for them algebraically. Okay, well, very nice. This is the region. It's the same region we're using in part A and part B. So now let us begin. Part A, revolve about the y-axis, which is here, and we revolve, okay? Well, if you want to do washers, this is going to be problematic. This would be slicing perpendicular to the axis of revolution, which would be like this. A lot of people like this in washers better, but I'm telling you why it's problematic in this part. Okay, so you'd have a little representative rectangle, you would have a delta y, you would be ready to integrate with respect to y. First of all, you would have to write both of these as functions of y, and this one, writing it as a function of y, is a little bit challenging, but more than that, there's this little part here where you'd have to write it as the sum of 2 integrals, because here the upper and lower are just 2 different sides of the same curve. So you don't want to, in fact, I wouldn't want to try to do part A with this or washers. It's going to be significantly more complicated. And this is why the technique of shells is so nice. Okay, so I'm going to use shells. With the method of cylindrical shells, we integrate, or the representative rectangle is parallel to the axis of revolution. And if I draw something like that here, my representative rectangle will be something like this, which has thickness delta x. And so I will have shells with respect to x, okay? So let's draw a picture of a shell here. With the shell, we have this, which is the radius. We have the height of the shell, and then we have thickness delta x. And this purple rectangle is right here, okay, from the picture. Now, how do we do volume of a shell? Well, what I always do, I don't try to memorize any formulas because I typically will mess them up. I just unroll. And when we unroll, we have this box, and like this, where we slice, unroll, and this length here is the circumference of the circle, 2 pi r. The height here is the same height, and then this is the thickness. So we see the volume of this shell is 2 pi r times h times delta x, like this. And now we need to read everything off the picture. Okay, well, the height is this height. And this is something you did like when you had area between two curves or something like this. It's upper minus lower. The height of the shell, I'll write it over here, would be x minus this, which we can slightly simplify. We get negative x squared. We get plus 4x and minus 3. This is the height of the shell. And then the radius r, that is, well, now I need a little x here. If this is x, it's this length. You go from the axis of revolution to this x. It's here, right? And it is in fact exactly x. Okay, this is x. So far, so good. So let's write out the volume of just a shell, and then I will immediately write down the integral. And this is a setup only problem. So this should be, just the shell is 2 pi r times h times delta x. Okay, this is the volume of the shell, length times width times height. Now let's just write down the integral. My total volume, okay, V is therefore, well, my limits of integration are the possible places that this representative rectangle can be. And that is from x goes from 1 to x equals 3. So I integrate from 1 to 3 of 2 pi x minus x squared plus 4x minus 3. And then instead of the delta x, which this is really the Riemann sum notation, we have the dx, which is the corresponding integral notation. And this finishes part A. Okay, this was shells. Okay, now we move to part B. Exact same region, and you even see I have it in the graph. What has changed is I have a different line. It would be down here. This is the line y equals minus 3. Now I can slice perpendicular to the axis of revolution. This is what I will do here. It's no problem. This will be washers. So in part B, this will be washers with respect to x. And I will have a representative rectangle. My picture looks very similar, except it's a different line I'm revolving about. But my representative rectangle is still like this, but this is now perpendicular to the axis of revolution. And now let's draw what a washer looks like. Just like I drew what a shell looked like above. Washers, we have this outer radius and the inner radius. This is capital R and little r. And again, let me get my pointer and look at the picture. What is the outer radius? Okay, and you see it here from the center, which is y equals -3, all the way to the top. So my capital R is not x. My capital R is x minus -3, or x plus 3. This is the length here. That's this length is x plus 3, okay? And then little r, it goes from the center to this right here, okay? In my picture, it's here, from the center to this. So from the center to this lower edge of this representative rectangle. Little r is this function, x squared minus 3x plus 3 minus -3. Or you can write it as x squared minus 3x plus, plus 3 is plus 6, okay? And then the final step here, well, first, actually, I'm going to do 2 steps. I take that back. Let's write the volume of a washer. Generally, what is it? The volume of a washer. We have pi, I'll write it this way, capital R squared minus little r squared delta x. Because this part here is, take the area of the outer circle minus the area of the inner circle is the area of this, and then you multiply, and I should label it, this thickness delta x. Okay, great. Now, so this is the volume of a washer. We have capital R, we have little r, and well, we're ready to write down our integral. I'll do this also in blue. My total volume is, it's an integral, again, 1 to 3, because these are, x goes from 1 to 3. This is where these rectangles can live. And then we have pi, we have capital R squared, we have minus little r squared, and then dx, okay? And this is part B. And this, again, just like part A, setup only, we would stop here. There is no need in a setup only problem to simplify this any further. Let's move on to number 9. This is the region bound by y equals x and y equals x squared. This region is not, it's going to be easier to graph this. But the interesting thing about this problem is both part A and part B, we have different lines to revolve about than just coordinate axes. In part A, we have the line y is -2. Now, this one is going to be very similar to part B of the one above, because you look, the regions look similar. I'm revolving about a y is minus something line. We may slice perpendicular to the axis of revolution, and this will be washers. Okay, so my representative rectangle here, with respect to x, delta x, and we have a little x here. And this will be, as I mentioned, part A is washers with respect to x. Okay. And, well, you can, in fact, I have a picture of a washer right above, so I won't redraw it here. Typically, I would every problem, but since I just drew it, we can see. Now, what's the capital R here? And what's the little r here? Because this is what we are interested in. Okay, here we go. Same kind of question. Capital R, it goes from here all the way to the top of this rectangle. This length is capital R. And you notice this is x minus minus 2. This is x plus 2, okay? And then, just like in the problem before, little r, we go from the axis of revolution to this bottom of this representative rectangle. And this occurs, the bottom is at x squared, that's this curve. And so it is x squared minus 2, which is x squared plus 2. And then you see this formula that we just discussed in the last problem is still the correct formula. So let's just write our integral down here. This would be an integral. Well, okay, maybe I'll do my limits of integration at the end, but we would have pi. We would have capital R squared minus little r squared. Uh-oh, I need to make sure you have the right parentheses, and then a dx. But now my x values range between x equals 0 and x equals 1. So the integral will be 0 to 1. And this is the volume in part A. Okay? Now let's move to part B. Same region, but we are revolving about the line x equals 3. Okay, so let me draw this now. So here is x equals 3, and we are revolving. Well, you really have choices here, and let me talk about the two choices. Number one would be to do something similar to what we did in part A of the last problem, where you see I can make my representative rectangle parallel to the axis of revolution. Parallel to the axis of revolution is cylindrical shells, and that would be something like this. This would be parallel. We see the axis of revolution. And then this would be integrating with respect to x. And this is perfectly fine. That's probably what I would do because I think it's easier. The other option, which will work in this one, but would be more, it would not have been a good option in the previous problem. But the other option is to slice this way, perpendicular to the axis of revolution. And then my representative rectangle would be like this. It would be a delta y, and this would be washers, again. But what I would need to do is write this as a function. X is a function of y. It would be x is square root y. And then I'd need to write this as a function of y. Well, that's just that x is y. And this would be a fine option as well. We would just integrate with respect to y if we want to do washers. But I think just to illustrate the technique of shells, and that's naturally how I would do the problem anyways, I will just do shells. So shells, we have a representative rectangle, we have delta x, and I'll write what I'm doing over here. This will be shells with respect to x. This is a picture of our shell. It's what I would draw every time I work a shells problem so that I don't memorize the formula per se. I just remember that I unroll and it looks like this, and then I just multiply length times width times height, and then I have the volume of a shell. But we have to be careful here. So let me label in my graph, this would be at some x. Okay, so the height here, well, just like the last one, the height would be upper minus lower. Okay, here, this minus this. The height is x minus x squared. But my r is what I need to think about. So if you look at this picture, it goes from the axis of revolution out to the representative rectangle. Okay, here, look, this is my axis of revolution, okay? So I go from here out to my representative rectangle. And the question is, what is this length? This length, oh, well, it's a lot. Maybe I'll just do it like this. No, it's not so big, but this length is our r. And well, what is this? It's 3 minus x, right? 3 minus x is this length, 3 minus x. Well, now we have everything we need because we know the volume of a shell. Maybe I will write it here, like this is different than I did it last time, but I'll write it with the 2 pi r h delta x, right? Length times width times height. And I could fill in my specific values for r and h, but I'm about to just write the integral down anyways. Okay, so my volume, I integrate. The x's run between 0 and 1. That has not changed. It's where my representative rectangles can be. And then I have 2 pi r h dx. Okay. This is what we get for this. Volume. Okay, as I mentioned, you could do washers with respect to y. That would be fine as well. But don't only know how to do dis and washers and think you're going to get by with everything, because it's very easy. For instance, in the last problem, it's very easy to ask questions that kind of force you to use shells. And so make sure you understand both techniques.
Here is number 10. We want to find the sum or show the series diverges. And this is more in the spirit of what we're doing in the beginning of the review, but I added this one at the end to practice a few things that we hadn't practiced in the other ones. So the first one, I'll just say we will find the sum. This series is geometric. We can tell by looking at it. And just as a comment, if you can't tell, let's write it another way. The numerator is 5 times 5 to the k. The denominator, well, we have 2 to the 3k. We can write this as 2 cubed to the k. So this is 8 to the k. And then I'll do one more step, and we should definitely be able to spot that this is geometric. We have 5 over 8 to the k. This is definitely geometric. We see it now. And we see our r is 5 over 8. Okay, absolute value of r less than 1 converges. Okay, but this question is more than just converges or diverges. We want to find the sum. We need a, right? But be careful here, because this starts at 1. And generally, when you have a geometric series, what you want to do is take this expression and evaluate at the lowest index that you see. A is the initial term. So when I evaluate this at k equals 1, I get 25 over 8. This is my a. Equals 25 over 8. And so the sum here in part A is, well, it's a over 1 minus r, which is 25 over 8 over, this would be 1 minus 5 over 8. This is 25 over 8 times, this would be 8 over 3. This is 25 over 3. And this is our answer to letter A. Okay, now we move on. I'll start B here. This should be a fast one, because look, quickly glance at the terms. What do you see? In the numerator, I have n factorial. The denominator, what dominates is an exponential. And we know factorial grows faster than exponential. So the limit as n goes to infinity of n factorial divided by 4 to the n plus 2, this will be infinity, which is not equal to 0. By the term test, this series, which is n factorial over 4 to the n plus 2, diverges. The term test, as I mentioned in class, this is one of the easiest ones to use, in my opinion. And we will definitely see that with part C. It's going to be more involved. But you have to be careful. The term test is also one of the easiest to misuse. We cannot ever conclude convergence using a term test. Okay, part C, and this is the last one for the review. Well, I really like this series. It's quite interesting. You might, just as a comment, you might think comparison, because we see a K and 1 over K harmonic series, but this square root ln K, well, for K large, this will be bigger than 1, and so we would have, this is like this. Less than something divergent, term by term. You can't use direct comparison. Now you also might think, well, we used earlier that the natural log is less than, ln x is less than x. And so you could replace this ln k with a k and you would have this. And now this denominator that I've just written is bigger. So I would go like this again. So this is why I think this series is interesting, because look, it's bigger term by term than something convergent. This circled is a P series, P equals 3/2, bigger than 1. And it's less than term by term something that diverges. So using direct comparison with either one of these won't work. We wouldn't be able to conclude anything. But I am not going to use comparison here. I'm going to use a test we haven't used yet in this review, which is, well, if you see an ln x and a 1 over x together, you think about integrating. So I'm going to use the integral test. Here, this function is, well, for integral tests, we need continuous, and we need non-negative, and we need decreasing. And it certainly is on to infinity. And so I may use the integral test. We move up, which will go like this. We integrate from 2 to infinity of 1 over x square root ln x dx. And this improper integral and the series will both converge or both diverge. So I can address the question of the convergence of the series just by calculating an improper integral. Okay, well, this is a limit. As b goes to infinity, we have 2 to b, 1 over x square root ln x dx. I hope you see what to do here. Substitution. U is ln x du 1 over x dx. And when I change my limits of integration, we go from ln 2 to ln of b. Okay, so this is a limit. As b goes to infinity, the integral, we go from ln 2 to ln b, and then we have u to the minus 1/2 du. Now I'm ready to integrate. Well, what happens here? Add a power, divide by the higher power. We get 2 square root u evaluated between ln 2 and ln b. Okay, one more, and then I can actually evaluate this limit. This is 2 square root ln b minus 2 square root ln 2. Okay, wonderful. Here we go. Now, this part is the only part that has a b in it, and what is happening here, ln b grows without bound. When we take the square root, it will also grow without bound. So this one is going to infinity, which says the improper integral diverges. Now, I need to make my conclusion by the integral test my series k equals 2 to infinity of 1 over k square root ln k. This diverges. Okay, and this is the end of our test review. Thank you very much.